All right, so again, thank you so much. My name is William Hahn. I'm going to kind of go over a little bit different view of what we just talked about, neural networks. But first, what I want you to do is, without hitting your neighbor, I want you to go like this. Neural networks, yeah. So this is what's awesome about like brains, right? You all just did that. It took like one verbal command, and you all had an idea of what I did. I did a demonstration and an apprenticeship, and you were quickly able to adapt that behavior. Robots can't do this. You got a whole army of robots. You want them to do something new. They can't just add behaviors like that. I found this is kind of cool. This is one of the earliest models of vision by Leonardo da Vinci here, and he actually thought vision was done in the ventricles, right? So in the middle of our brain, we sort of have this empty area filled up with spinal fluid that sort of nourishes our brain. He wasn't quite sure, and he said, yeah, that's probably where vision's happening. We've made a tremendous amount of progress in the last few hundred years to actually figure out how our brain works and what these things are. So we're going to talk about neurons, neural networks. What is image data? Why are these patterns? What is this idea of a loss function, and then optimization. So basically the same thing we just discussed this morning, but just in some slightly more detail. So what are these things? Well, they're apps, right? We want to create an app that does something. I want to be able to take in a photograph on this app, run it on my phone, and I want to have it output what the name of that car is, for example, or the species of the animal that we're looking at, or the expression and the emotion of the person that we have a photograph. And so we want to go from millions of numbers. Your phone has megapixels, millions of numbers, to a single number. Is there a dog or cat, 0 or 1? So how do we sort of mathematically throw away all of these numbers in an intelligent fashion? And as we saw how the visual brain is sort of breaking things down into edges and common parts and features to kind of see how that part works. So as we said, this is not new. This is actually very, very old, right? It seems like this stuff just got here, but these ideas actually go back, more than 167 years. So when I came across this, I was shocked. This is Alfred Smee in 1850s. The theory of electricity was less than 100 years old, and he thought, well, let's see if we can combine this electricity idea with biology and figure something out about reason and instinct. And this is a plate from that book. This is actually upside down, but it says body, nerves, and brain. So this is a model from 167 years ago of how our brain might actually take in the signals, right? This says skin, ear, and eye. And here we see the eye going through some nerves to something that you should recognize now already as a neural network, and then that's going to then send output to the muscles here. So I think this is extraordinary that so long ago we had a very good and a very modern view, right? So if we take that and sort of look at it, this looks just like a modern neural network today. So as we saw, the inspiration has come from cellular biology. So neurons are cells. They're just like any other cell in the body. But like an amoeba, they can sort of take one side of things and sort of stretch it all the way out to the extreme. And if you ever forget what neurons look like, just go like this, because you have a map right here, right? So you have your neuron, that's your body there. You have your inputs. We have 4 inputs. Then we have this other input called the bias, which is just sort of there all the time. Even if the inputs aren't even turned on, this bias is still going to be there influencing things. And then if all of that stuff, the bias plus the inputs, if all of that is bigger than 0, then you're going to get a 1 going out the other side of this neuron. So we can think of this mathematically as taking in some kind of input, weighting it. I want to consider how important is that input. Some inputs are just not important. So I could assign a 0 to that weight and say, just ignore this. Or I could say, this is very important. Really consider this number here. These numbers might be from, say, a weather station. We have a weather station on the roof. Now I want to know what's the chance we have a hurricane force winds in the next 24 hours. So we could feed in one number might be the temperature, one might be the pressure, one might be the wind speed, and so on. Another input might be the day of the week, like the fact that it's a Tuesday. Do you think that matters for a hurricane? The fact that it's a Tuesday, like does weather care about the day of the week? No, it doesn't matter. So in the network, it would learn to put a 0 on the input of the day of the week it is. Other things like economics and stock market, it might really matter that it's a Tuesday. But for the hurricane, it probably really doesn't. So we can have the neural network figure out how important each input's going to be. And then here we got 3 inputs, and then it's going to add those together, right? So this, if you're not familiar, this giant E just means we're going to sum things up. So we're going to take a weighted sum and add to it the bias. If all of that together is a positive number, then this neuron will output a 1. Yeah.
Curious, what happens if, for example, you said that like the hurricane on a Tuesday that may not be correlated? What if that Tuesday is correlated to a lunar calendar that something else is correlated?
Yeah, so it might be that somewhere and it found, well, this is a very special Tuesday or something like that. That it's not actually that it's a Tuesday. It has to do with the fact that it's the double moon of whatever, you know.
So knowing where the Earth and things are
Right,
related,
right.
maybe that has an effect that we don't know about.
Absolutely.
And here, that would be another.
Say again.
Cars, 7-day dust cycle actually affects it.
That's true. Absolutely. And like the rain patterns are different in cities on the weekend and stuff like that because of traffic. So it's certain, you know, it absolutely might matter. So that's what's really neat about this is to let it run, go back and see what's the weight that was given to the Tuesday. And then look at that and say, does this thing think Tuesday is important? And say it does think that Tuesdays, maybe there's something about Tuesdays that we don't understand, right? So that can give us more insight about what to look at. So this is pretty neat to see that going back, these things actually go back to the 80s as well, to something called a neocognitron. So you can see these moving like earthworms. In the course of 15 minutes, you'll have neurons that have never touched or talked to each other that are wiring up. Hopefully throughout the course of this week, you're having new neurons that are connecting and allowing you to understand things you couldn't understand before. This is from 1980. So even though this is like 35, 40 years old, it's going to be very similar to what we're working with today. Right, so the idea is that in the old days they talk about a grandmother cell, that you'd have this one cell that when you saw a particular pattern like the face of your grandmother, you'd have this one cell and you say, oh, I know who that is. While this works for deep learning and neural networks, that's not going to be how the brain actually works, because then something like that happens and you not recognize people. So it's not going to be that it goes down to one cell. And mathematically, we're going to do that. We're going to clap something like the letter B, and it'll go to this dot, and then something else will go to a different pattern. And so even if we change the size of this and move it around, it will still be this one single neuron that activates. So in the brain, it's likely that populations of neurons activate, but we can sort of model that and imagine that there is this sort of one cell that's going to light up at the highest layer when it sees a particular thing, like the letter B. I thought this was pretty neat. I found this from 1925, Elements of Physical Biology. And so they have this mechanical walking beetle, right? Elements of a correlating apparatus. So somehow, this is a very early, model of this kind of stuff. But I love this in that we want to build a model system, right? And so in simulation, you want as many details as possible. In a model, you want as few details as possible. We want to get at the core, the essence of this. And so we try to follow this type of research. This is an interesting one by Gray Walter. So it's interesting to see with this AI winner, a lot of this sort of style of science went out of favor. Does that look lifelike? But this is the first start of this, almost the cybernetics era, where we want to build, intelligent machines that can interact with their sensors, and then change the motion, the motors that they activate, essentially to become alive. Roomba, right?
Yeah.
It's like a 75-year-old Roomba. You can imagine there's sort of all these types of experiments. And this thing was very simple, but it could, very first, foray into this idea of using robots not to do engineering per se, but maybe to do science, to think of these as model systems. Some of our colleagues in the brain science and the neuroscience department, they use animals, right? They have mice and rats and things, but there's some stuff that's just not practical or possible or ethical to do with an animal model, right? If you put the mouse on the maze and you put the cheese over here, and then you bring the mouse in again tomorrow morning, it will go over there thinking there's some cheese there. You can't erase that mouse's memory. But with the computer, our little robots, we can just wipe it out so that when it goes in the track, it's as if it never had seen that track before. So it allows you to experiment in a way that's just not really possible otherwise. So what we want is we want something like this little Wally that's going to take in all kinds of sensor data. It's going to have cameras for images. We want it to also be able to understand video. There are actually conditions in the world where individuals don't really perceive motion. They see the world as like a sequence of static images. But most of our brains can process video, which is going to be very important. But if you try to take, to remind you how early we are in this field, if you were to take like a film, say like Jurassic Park or something like that, and you want to load the whole thing into memory, forget about it. You can't actually fit that much information into the computer at once. So we have to have ways of sort of looking at the movie. We don't watch the movie all at once either, right? We see it one frame at a time. We want this to be able to take in laser scans, text data. We're talking about like if it's a Tuesday, if it's a stock market, and there's something happening in the press, and people are talking about this and that, about this product, then suddenly this little bot can say, hey, you know what? I want to go and I want to invest in such and such because I saw a picture of a new product and I saw video being really excited about that new product. And there's an article, there's 10 articles about this new product. And I heard some audio of people speaking really excitedly about this new product. Let's invest in that new product. So this is the kind of scenarios we're going to see very soon. To see how things have changed, this is the 2004 DARPA, the Defense Army Research Projects Agency. They put out a challenge for this desert. Audio is not relevant. So they put out this challenge. $1 million prize is to see who can get this car to go across the desert. They put it in the desert because there's nothing really to run into. You're not going to hurt anybody. But these enormous contraptions where they threw everything they could at it, it didn't work, right? It didn't work. Not one of these entries. These are the schools from all over the world. Not one of them was really able to get it, their car to go more than just maybe a half a mile or something. Most really just made it just not much farther than the start line, right? You see that one got a few hundred yards. There's a little miniature one. There's one sort of crashing into the wall. This is why we research with miniature cars, right? I don't want to be anywhere near a full-size vehicle when we have students debugging the code. So what's so exciting is these things were very expensive. You can see there's there's $1 million prize they're handing out. There's big lasers and radar domes and all kinds of sophisticated sensors on there. What we're trying to do is, can we do this from just a camera? We know we use things like more like this, much safer. I don't want to be anywhere near this thing, right? What's the purpose? If you can get it to run little, then you can scale it up to something like this. But this is representative about the state of the field in 2004. So if we go ahead a short 10 years, to 2014, Audi put out this race car here. Who can drive a race car? Who can even drive manual? Notice there, he said it's being controlled. He didn't say it's being controlled by the artificial intelligence. Right? Let's go back and use the word he said. Right? The artificial has been dropped. There's two cameras here. Stereo vision, just like you have when you drive a car.
Are these doing better than humans?
I don't know. I didn't look at like a lap time or anything. I kind of doubt it.
Wouldn't it make sense that this could optimize everything and should essentially better than any human ever can?
Yeah, with enough track experience, it could do like a tighter line. What's really neat is if you look at the winners of competitions like this, the winner has the curve that matches the closest to a cubic spline around the track. So you can imagine mathematically it could find the optimal, but I don't think they're winning the
You made the comment that he dropped the artificial intelligence.
Right.
I'm curious what definition you use for intelligence.
Yeah.
What definition you use for artificial intelligence.
Yeah, it's a great question. Well, I guess we got to go back to the beginning with that. You know, Turing proposed a simple one. And in modern terms, we could say it like this. We're going to put two telephone numbers into your phone. They're both going to start texting with you. After about 20 minutes or so, you have to decide which of those phone numbers is a real person and which one's a fake person. So this was Turing's definition. And it gets into real philosophical things because how do you know this thing's really alive? It's just having a chat conversation. There's another one named after Ada Lovelace, and this is a thing where it says the computer has to do something that surprised us, something that we haven't really thought of. And then there's another one. I think it's Mitchie put this one out, and it's can it get a job? Right? Can it go out and get a job? Right? What's that?
That's easy for a robot.
Exactly. So depending on which of these sort of flavors of threshold you like, we passed some of them. And I think that's more of a philosophical thing. So let me think about that, and we can get back to it.
The reason I asked, I did a course back in '85.
Yeah.
Sorry, '83 on artificial intelligence. This is when expert systems was the state of the art.
Right.
Which now we laugh at.
Right.
Sure. And the consensus of the class was two things. Was that an artificial intelligence is a self-aware sentience that knows it is distinct from others, and that it will not happen in our lifetime.
Well, you know, so you said, you know, self-aware, sentient, aware of themselves and others. You know, do 3-year-olds have this? 2-year-olds?
Some of them do.
Some of them do, right? Do animals have this? So it's like we have different categories. One thing that I think is really interesting, I love to go back to all these, you know, 80s kind of videos to see what AI was. And if you go back, like the speech to text, like, what time is it? Oh, it did the whole speech to text. I hit the button too early. But you know how that works, right? That kind of thing. If you went back to the 80s, they would have said that is AI. They would have said this is AI. So part of the problem is that AI is a moving target. It's kind of a victim of its own success. Anytime something works, they scrub off AI, even scrub off the intelligence, and it's just a product. And you just sell this on the market, right? So lots of things that we use. In one of the things that Elon had up, there was an Adeline, was this brief model after the Perceptron, but before the deep learning. There's an Adeline in every modem. There's a single neuron stuck in every modem to try to figure out the noise level. So these things are all over the place. It's just that as soon as they get here, we no longer think of them as this thing worth talking about called AI.
I would like to go beyond that question. Are we really intelligent animals? Because so let me put this where is the driver?
Where is the driver here?
Yeah, watching TV.
Right. Well, this one, the driver is going to be a mathematical, you know, package that was developed by humans. So you get into the philosophical thing of like humans built this brain and all that kind of stuff. But I think the important to remember is this thing is able to go around at 150 miles an hour. Good luck getting it to find a parking spot at FAU, right? we're not there yet. I mean, we have these little tricks and we have these little kind of gimmicks and stuff, and it's extraordinarily exciting because problems that were just impossible 10 years ago have moved from impossible to practical. And so it's really this shift of impossible to practical problems that I'm really excited about. The overall thing, when are we going to really get intelligent, alive, awake machinery? You know, these are good questions. I don't know. I think what the most exciting thing for me is the captioning system that Elon was showing this morning. You can take in the image. It will provide an English sentence. 25% of the time now, people prefer the sentence that was generated by the AI. Now, if you had asked me, you know, 15, 20 years ago how you would do something like that, I'd say, okay, easy. You get the fastest super quantum computer in the world, and you use that to simulate chemistry. And once you've simulated chemistry, you can simulate cells. And once you've simulated cells, you can simulate living beings, and then you can raise a living being in this virtual world, and you can poke it and ask questions.
Yeah, you're playing God.
Right? Yeah, that's what I thought you might need to have this kind of stuff. We would need something like C-3PO, something like R2-D2 or Data from Star Trek that was alive and had experience and lived and interacted in the world, and we could query that thing and ask it about questions. This captioning system that's taking in photographs and providing you English, this is a giant Excel spreadsheet. You could do this in Excel. You could have one column. The first column is your photograph. 4,700 columns later, you have the output as an English sentence. It's just numbers. Just numbers. Now that's weird in terms of getting to the what's intelligence, right? Because am I not captioning my, scene that I see right now? Am I not generating English sentences based on the context and the signals that are being provided to me? So I think this is very strange in terms of the philosophy of the brain, that now we have a proof of concept, a simple, sufficient conditions, that if you want to take in photographs and map it to English, all you need is numbers, which is really strange. You don't need awareness. You don't need internal experience or anything like that. And these are strange notions, right?
The real thing is that reality is always uncertain,
Exactly.
How are you going to interfere?
Yeah, exactly. So the uncertainty, I think, is really the big breakthrough with neural networks, compared to going back to the 50s. I like to say in the 50s, we were trying to build a blind logician. We wanted something that was completely blind because they didn't really have TV cameras hooked up to these things at all. And they wanted it to do logic. But that's not really how people work, right? One thing we know about, education, children and people are not logical. They're not logical. I saw someone who was, sort of complaining about the deep learning result with the caption, and they complained that some of the sentences weren't grammatical. Do little kids speak grammatically all the time? I don't even know if that sentence was grammatically correct, right? So I don't think that's how real human beings communicate. So I think that dealing with uncertainty and chance and randomness, that's really the power of these new systems. So, it's 2014, these things weren't really out here. Now you can buy these things at the mall, right? They're here. They're here now. So what is this machine perception? Well, we want these cars to be able to do things. Well, they have to know what stuff is. They have to recognize things like stop signs and staplers. We were up in the office a month or so ago, and somebody came in and they said, I'm looking for a stapler. Do you know where this is? And I wasn't even in the conversation. They were asking someone else. But I was able to hear what they were saying, understand the words, the features of the language in English, just like you're doing now. I recognized who was talking. I said, oh, hey, Paul, I know where a stapler is. I was able to dynamically shift my attention to their conversation, recruit knowledge that I didn't really know I had, right? I knew where the stapler was in the office, but I wasn't really, it's not like all morning I was like, I know where the stapler is. Yeah, let me keep remembering that. Like, wasn't important. And then I was able to, action, reach out, find the stapler, and hand it to them. We're nowhere near that with robots. To have a robot just like sitting in your office and you're talking to your coworker and you have a problem, the robot's like, oh, I know how to fix that, right? That's just not even close, not even close. This is what's so exciting about getting involved in this field, because you can make that kind of stuff happen. That we want these things to understand their surroundings, to not bump into people, to be aware of all the people in the room. There's technologies now that you can get on the market where there's a camera and it registers the emotion of every student in the room. And so now I can get an automatic feedback report about, what did you think of the lecture? Right? I'll just know. I can ask the system. It's not running now. So we're used to, robots like this. They've been on the scene for a while. I think, they kind of got this right with this gold robot here, because he talks about how he was the translator. And he could translate between all of the other robots. So if you ever try to set up a printer to a computer, it's not easy to get robots to talk to each other, right? So we're going to have one robot that just deals with all the other robots. We're working upstairs was, can we plug wires into our brain, right? This person's a robot, but can we hook up a wire to our brain? Or at least maybe not plug into our brain. Much more better if it's sort of like a ball cap that we can wear. And there's the idea that we'll be able to type, 100 words a minute with just a sort of a ball cap. And for some people, that would be a game changer. We're going to see sort of like, healthcare robots that are going to be able to understand what you've said to it, how you feel. It's going to know the symptoms. It's going to remember everything you've ever said to it, right? Go to your general physician and say, do you remember what I said to you last time? I mean, they might have some notes or something like that, but they can't possibly remember the words you said, how you said them, how your voice sounded as you said those words. So this is the kind of things for therapy and for traditional medicine is going to be extraordinarily important. And also things like senior care, right? This is a funny movie called Robot and Frank. And Frank's sort of losing his memory, so his family gets him this robot, and then they get into some mischief. So kind of a fun thing. So we'd like to think of robots, as model organisms, as a substitute for the lab rat, really, right? That all of neuroscience for so long has been based on these model systems. Some people use fruit flies, some people use rats. Increasingly less now is primates. It used to be, 20, 30 years ago, lots of labs had sort of primates, and they would, poke at them and things like that. It's just prohibitively expensive now and not really practical, right? It's cost millions and millions of dollars to get those animal studies. And at the end, what have you really learned? Right? Yeah.
So what about the human beings that are not the norm, where there are people that do have identical recall? Things like that. How do we take that into account in these types of models?
Yeah, so like sort of the edge cases, the people who can memorize pi to 500 digits, or know that, you know, if you make up a date in the future, it'll tell you it's a Tuesday, right? The people who can do this kind of stuff. These edge cases are fascinating. We don't know how they work. And most of the breakthroughs in understanding the brain have come from sort of the failure cases or the edge cases. Like the famous guy who got hit in the head with the tampering iron in the railway, and he's got this big giant rod through his head, and he was okay. His personality changed, but he didn't die, right? Yeah, exactly. And so, you know, that was like a big breakthrough. Like, wait, what is this whole thing, and how does it work? And so I think some of these sort of edge cases can be very, you know, insightful, and we don't really know yet how these things work. There's like one kid who learned Icelandic in like a week, right? That you might be familiar with. It's like, how does that kind of stuff work, right? That's what they call like zero-shot learning or one-shot learning, to be able to pick up something in just one go. Most people, it takes longer than that to take in something. You have to kind of repeat it over and over again.
For the people that can tell you the day that you're gonna die.
What's that? Yeah, I don't know. Maybe the life insurance companies are going to be interested in this deep learning because they'll be able to do just that. So we use these rovers as a model system. We can reconfigure their little world and test to see, you know, how do they navigate this, right? In the animal experiments, they'll put the mice in the maze and they'll time them to see how well. And just like as we saw that Claude Shannon was trying to do almost 100 years ago, we want to kind of rethink this science of robotics. And that allows us to formalize this theory of the brain. We want to think of the brain as a control system, as the sort of the mind of an AI. And we want to do two things. We want to understand the actual human brain, and then we want to just build copies of brain-like objects that we can use to drive cars and help us with medicine. And in general, we're going to have this basic loop where we have the brain, which is going to take a state from the world, the input, the screen of the Atari screen. And so some of the breakthroughs have been using these old sort of 70s video games and getting a modern supercomputer to learn how to play this. So this is just a bunch of pixels. As a human, even as a little kid, when you sit down in a game like this, you're bringing a tremendous amount of knowledge to the table. You know that you're the little spaceship or the Pac-Man. You know that your little controller is going to move it left and right. You know that you're not this little zero. You know that the scores go up. Like all kinds of priors that you're bringing to this that the AI doesn't really have. But what you can do is you can have the reward signal, this number, fed from the machine, and this is reinforcement learning. Then we want this brain ultimately, when it learns, to be able to choose the appropriate action, which will go into the world. And then from the world, the world returns to you a reward sometimes. You don't always get rewarded. Most of the time you don't. And then you're going to get a new state. And from that, you want to then choose a new action. So like in something like Pong that we've been working with, you have a very simple world, as you know, and this has to move up and down. So we want a neural network that's going to take in all the pixels over here. And then it's going to consider them all as in these layers, these neural networks. So it's going to continue, look at the features like Elon was talking about. So we have the different size lengths of the bar. This one's really small, so we can know that that's the ball there. And then this one's the paddle because it's slightly larger. And so through these layers, it can learn to understand what these different things mean. And then from the output, this thing can have the probability of the paddle going up versus down. So this was a big breakthrough. This is the group DeepMind out of the UK. It was a small group, less than 100 people, and they built this system to take in the video game, break it down into convolutions. We're going to talk a lot about what these steps are tomorrow. Then from the convolution, you get to a fully connected network. This is the ReLU that we mentioned that we're going to discuss more. And then from that, you have the output of sort of which button to press. You can press up, you can press left, you can press... Atari is simple because there's only the directions in the one red button. So you get the different directions, and then you get the button, and you get the directions plus the button. And so this is sort of a very simple brain that's going to have to choose action choices, right? Your sort of controller for the world is almost millions of dimensions kind of thing. It's much, much more complicated than this in terms of the output, but the basic framework we can use for almost anything where we want to take in an input of some kind, photograph, and then choose an action. This might be the camera coming in from the front of a car, and this would be the steering wheel. This also, in long term, might be an MRI image, and this might be a chemotherapy treatment course, right? So you could have like a full end-to-end that would recommend treatments. So this is sort of where we're at today in terms of neural networks. If we look back up here, this is our neural network from Alfred Smee from 1850. And Russ, you were asking about can the network sort of pick the architecture? So these are some of the more famous architectures in the world. Here we see the first perceptron, and we have a feed forward neural network. And we add more of this green layer, we get to a deep neural network. And then we have some really famous ones, right? And so we have the convolutional neural network, which we're going to spend tomorrow talking about. There's recurrent neural networks. The most famous one is the long short-term memory. And then you've got some more exotic things like hot field networks and Boltzmann machines that are more like from physics. Liquid state machines and extreme learning and echo state we're very interested in because these have to do with random numbers. So we've been doing some research with these. And then we'll talk about deconvolution tomorrow as well. So you don't have to like pay any attention to this, just that I like to think of this as maybe an early periodic table, right? When Mendeleev went out and he said, there's these properties amongst the chemicals, and if we put them in this chart like this, we can kind of see some features. I think we're just getting to that stage where we can figure out like the basic motifs of these brain functions. But you can very easily just imagine yourself picking up a few of these that have never existed, plugging them together, and then you can name it, right? It'll be hard to imagine that this is all the architectures that's going to exist. This has to be just the beginning. Sort of a Cambrian explosion. So this is really neat. We think of perceptron as two things. It was a mathematical model. It's still at the core of deep learning today, but it was actually a physical contraption. It was a machine. They didn't have the digital computers they had today. So they tried to sort of make things with like a dimmer light switch that you could turn the light switch and the lights get dimmer. They had one of those, and that represents the weight. How dim is this input? And then they actually had little motors connected to that would turn the light switch, right? So this person one at a time is presenting this machine with a slide, and you saw they gave the answer and put right or wrong, right? So you can imagine how slow and tedious that would be. Now we can do the same process with a computer loop, thousands of times a second. He says right or wrong. He's sort of flipping the switch. He said, while promising, this virtually died out, right? This sort of just the AI winter, and people stopped working on this. This is the Alvin Project that's been an inspiration for us for the little car. And so we'll see in some slides in a minute that there's a television camera up front, and this unit was able to digitize the road a couple times a second. Right? So even if the color of the road changes from rain. So the idea was, he said, the researchers don't yet know how nets learn. And so for a long time, the sort of main argument was, well, these things are a black box. We don't know what it's doing, so we can't use it. It's not safe. We can't validate it. We're not sure what it's really willing to do. I think a big breakthrough in that has been starting to show the computer images. And when you teach it things like cats and dogs, and then you open up this black box, well, what do you find in there? You find things that look like cats and things that look like dogs. So I think the argument is that we don't know what this thing is doing. I don't think makes any sense anymore. We now have the tools to go in and look at what those neurons had learned. And it's very obvious that this thing is looking for a blue edge at this direction. This one's thing looking for a red triangle corner at this angle. You know, so what's the big deal, right? Why is this suddenly that you can get these cars? I think it's so exciting. You know, that car they just had. This thing cost millions of dollars. It was a big army, you know, ambulance that you retrofitted. You had to have people with computers. The computers were the size of refrigerators that went inside that. And now you can replicate that experiment on your own for like, you know, $100 or something like that. So it's just extraordinary that you can kind of jump in. We saw this graph this morning. This is right how many 21 billion gigabytes crossed the internet when I joined FAU in 2011. And then since then, it's grown by like 4 times. And so this is the world when you think that you guys, as the students, right, where are you going to go get your job, right? You're going to be getting an employment out here somewhere. What does that world look like, right? I was talking to someone recently, and they were talking about these machine learning things, and they were saying, well, how do you know it's working? And we're talking, and they said, well, we'll just check it. What do you mean you check it, right? You can't check it, right? You've got 27 million pictures of cats. What, are you going to go verify that each one was actually a cat? You can't do stuff like that. We have to think about it different. So, you know, every minute, 72 hours gets put on YouTube. To me, that's like a time machine, right? It's like where minutes get stretched into hours. That's crazy. Now imagine it's your job to verify that, you know, copyright music doesn't get posted on YouTube, right? So you're sitting in YouTube's office and you're going to go through all the videos that get posted to make sure there's not a copyright song. Well, your first minute in, you're 72 hours behind, right? You can imagine having that kind of job. Right? You come back on Monday and finish. All right, if you had, you know, Facebook, right? I like to imagine some Facebook in you know the 80s or 90s, right? With the piles of, you know, Polaroids and volunteers sort of sitting them out on pin boards, like, oh, it's Jimmy, and like, you know, pinning it onto some wall. It wouldn't possibly work that way. It couldn't possibly work. We have to have the AI sort through these 300 million images, and this is nothing compared to what we're going to get with medicine, right? We're going to get way more than that. So of all the data of this 83 gigabytes that crosses the web, 86% of that is visual data, which traditional algorithms can't really do much with, but these deep learning systems can. So what are all these images? Well, the pictures of people's cats and dogs, of course, right? This is what people put on the internet. So they when you let these things go on the internet and you let them sort of look at all these pictures, they come back with things that look like representations of cats. So say we want to build an app, we want to be able to sort out cats and dogs. This sounds really trivial. We were looking at this morning about the easy problems are hard and the hard problems are easy. right? What's a hard problem that's easy? Well, doing like integral calculus, right? So if you go over, you study mathematics and you go and you take freshman calculus, you have to learn how to do these integrals, which is this crazy branch of mathematics. It's not easy to do. In 1960, they were able to write a computer program that aced the MIT integral calculus exam. Did better than students. 1960. The AI was able to cross problems like that. But yet, when it comes to cats and dogs, it was only a few years ago. Very famously, in 2007, there wasn't a computer in the world that could handle this problem. Not one anywhere. And that's not true, right? That's not true anymore. And so we've gone from this impossible to practical, almost overnight. So what is it from the big picture? What are we trying to do? Well, imaging is when we take sort of the real world, let's say physics, and we turn it into an image. We want to create an image with a camera. That's what cameras do. Image processing we're familiar with. This is like filters, and you can make sepia and black and white, and all kinds of stuff that we can do with our phone, where we take an image and you're going to go to another image. Computer graphics is when you create a video game. What you do is you type in a bunch of code. You're going to type a bunch of symbols, and those symbols are then going to get converted into images, like Pac-Man. So that's computer graphics. Computer vision, we can think of the opposite of computer graphics. We're taking an image and we want to turn it into a symbol. We want something like a very abstract thing of cat. Your brain knows what this is. It can see it. But for a computer, that's almost impossible to figure out what that is. I'll pull up an example of that in a minute. So what we want is a system like this where it's going to take in the pictures and it's going to output and say this is a cat. But the question is, what are these wires, right? So there's sort of, one problem is we got this whole thing. All right, we set up this thing, and if the wires were working, you would do this, right? So we have to figure out first how we're going to set up the architecture. But then we have to figure out, well, what's the strength of these blue lines? These blue lines are these weights, right? These weights and these biases we've talked about. Those are like little tuning knobs. And you have to figure out what each of those are. And so that's what we're going to have the computer to do. So we're going to give it a bunch of cats and dogs. It's going to break it down into features, like we saw the different size features. It's going to try to look for things like feet and eyeballs. And as we'll see, it sort of builds up these representations. And then ultimately, you give it a new cat, and it's going to say, this is a cat. So there's sort of two halves to the machine learning. We have the training, and then we want to deploy it to make inference. So this idea of inference, right? It's not really, normally we think of like calculating and stuff. This is, we're trying to infer, right? What was this thing that fell onto my eye? Like, what is the thing in the real world such that I would get this picture into my sensor? So a breakthrough in this was the creation of ImageNet. And ImageNet is sort of a challenge. It's a collection of more than 1 million photographs taken from 100,000 different categories. So this isn't just dog and cat. This is like Australian sheepdog and Siamese cat.
More than that, you said, what is this thing that fell into my eyes? Is it a cat, or is it just a name that I apply to the...
Yeah, like what is this thing in the object? Like what we want to know, like I'm getting some sort of sensory experience. How do I explain that based on what might be in the real world? And so this having this concrete challenge was a breakthrough, because you want to be able to say, this is a container ship, this is a motor scooter, this is a leopard. This was the problem that was just very, very difficult until recent. And so why was this so difficult? Well, the old AI was what it says rule-based systems, where you're going to take an input, you're going to get experts that are going to hand design a program, and then that's going to create your output. And so you sort of think about it. We're going to use all our brain power. And this works, but it's very difficult to do. It takes a lot of money. It takes a lot of time. And for some things it works, and some things it just doesn't work. So for driving a car, there's really no hand-designed program you're going to be able to write to drive a car. I mean, think about handwrite programs. Like, if there is a stop sign and it's on the right side of the car and it's approximately this big and it's not a hurricane, it's like what? You'd have to add like all of these, conditions, right? But if it's an emergency and you're on the way to the hospital, then you can go through stop signs. Or if, right? You can't do it that way. And that's not how real humans drive. We have like a booklet when you go to the DMV to take your practice test. But the real test is like, can you drive a car, right? And what do? They put you in a car with a dummy steering wheel, right? So the other person has like the brake and the steering wheel. So they can apprentice, so that you can figure out, and if anything goes wrong, they'll sort of take over. But you have to sort of experience this on your own. You can't be told how to drive a car. In the same way, you can't be told how your ankles work and how toes work. It's not how you teach little kids to walk. If you want a little kid to walk, you get on the other side of the room, you sort of smile at them, with something, and then hopefully they're going to kind of wander over and you go, yay, when they make it over across the room. You can't actually tell them how your toes work. You don't know how your toes work. You certainly can't communicate that to them in English, right? If you think about your toes too much, you'll probably fall down the stairs. So classic machine learning says, all right, well, what we'll do is we'll take the input and we'll hand design features. That's what we'll do. We'll say, let's break it down into edges, or let's break it down into different colors, or we'll break it down into different sounds of bass and treble. We'll think ahead of time of what these features are going to be, and then we'll let the computer decide what to do with those features. So this is the classic machine learning. Representation learning says, well, let's take the input and have that learn the features, and then we'll learn the mapping from the features to the output. And then finally, with deep learning, it's just basically we're going to do this on more than one level. Then we're going to have it first to say, hey, you know what, I think the world's made out of edges. And then the next one say, well, edges often combine into things called corners and arches. And corners and arches often combine into things like eyes, because you have an arch up top and another arch in the bottom, and then you have this shape with a hole in it. So you get these combinations of features that can ultimately build up to the output. But if you notice, the hand design part has sort of been scratched from this list. So I was watching a talk by the inventor of convolutional neural networks, Jan LeCun, who we'll hear a lot about tomorrow. And he's saying that when we write traditional programs, when you write your hand design programs, you're making assumptions. You're making assumptions about what the world is, how it works, what it looks like, what's important. But when we let the computer decide these features, we're making fewer assumptions. So this was the ImageNet, and this was the breakthrough. We can see down here, here's the hand-coded features, 2010, 2011, 2012. They were getting sort of about 74% accuracy on this test, right? Hardly passing. And then in 2013, we see this introduction of deep learning, and we get this incredible just jump, right? Everybody in the field the next year switched over to deep learning because there's no amount of tweaking. I mean, people have literally abandoned this stuff because they realize that there's no amount of tweaking this that's going to get you that kind of improvement. And then you can see what's interesting is the human threshold there at 96. A couple years ago when I was teaching here in the physics department, I sort of put this on the board, and I was like, because we were still at this dot here, and I was like, everybody, this is going to cross this line in the next year, and it did. So here we see another representation of the same thing. So this is the classification rates. We want this to go down to make fewer mistakes. In 2010, they were still making 30% error, something like this, 25% error. And then we can see this massive jump here when the introduction of deep learning with this AlexNet that we're going to be talking a lot about this week. So when you leave this week, you're going to know how to run your own AlexNet. I would argue this is sort of one of the more important sort of neural networks that was ever developed, and you're going to know how to run that. And so you can see here is the human performance zone. This test is really boring, right? There's 1 million images on this test, right? 100,000. You know when you take the bubble scan-shon, and it's like A, B, C, or D? This has 100,000 little bubbles, right? 100,000. So for each photograph, you have to figure out which of the 100,000 little bubbles you have to bubble in. Who wants to take this exam? You wouldn't take this exam. You can't take this exam. There's a million things. You can sample it. So real human beings won't do this, but you can get graduate students to sit down and take some of these tests, and they'll figure out how they can label some of these. And when you have people do that, they get approximately on average, this 5 to 10% error. So what's happened since 2015 and now 2017, we're past what you could say is superhuman performance. Do these things see as well as human beings? Absolutely not. So much of our vision is very dynamic and very rich, and we're capable of doing very, very many different things in very weird and strange circumstances that neural networks still fail miserably at. But in terms of solving that challenge, this Scantron test of 1 million entries and 100,000 little bubbles, it's right there. So what happened? What happened? Well, so here see the error rate jumped from 26 to 16. That year, 4 GPUs were entered into the contest. The next year, everyone sort of got wind of this. 60 GPUs had the entry, and then the next year, 110. And deep learning, the first approximation, is applied GPU computing. All right, this is what the field is sort of learning how to do this type of math on these types of cards. It's interesting to note, in 2011, I started looking at GPU computing, and it was too difficult in the sense that if you had a math problem and you wanted to run on this video game card, you had to take your math problem and restructure it like it was graphics of colors and vectors and all this kind of stuff and angles, and then move it back into the math world. It just kind of made you dizzy. And what sort of happened here is there's a sort of a new interface on the code, which you can just write mathematics. You can say, take this list of numbers, multiply it by this list of numbers, give me the answer, and it will go and figure out how to make it run on that machine. That was the big breakthrough, is that you don't have to think about how this thing actually works. You could think about the mathematics, and this will automatically compile. So this is what we were talking about this morning, this pattern recognition. So we saw that the computer was twice better than humans, 3 times better than the closest artificial competitor, and 6 times better than the best non-neural method. And so this was in 2011, Jürgen Schmidhuber out of Switzerland. So why deep learning? Well, as we increase the amount of data, we want to do cats and dogs. If you give it 10 photographs, it's not going to work, but it gets better as you give it more. But other algorithms, as you give it more and more data, it just kind of flattens out. It just doesn't keep improving. Whereas deep learning, the more data you give it, the better it gets. So right now, it's going to be who gets the data first. The architecture doesn't really matter. There's another plot, I don't think we included in this one, but basically they have like all the different architectures, and really it's the amount of data that matters. Yeah.
What happens if you give it bad data? Will it still continue learning good?
No. So the classic expression, garbage in, garbage out. Right. So if you give it bad data, then you're gonna get bad inference. And this is actually a security concern. So I was talking about like the stop signs. What if we're training a self-driving car to stop at stop signs, and you have this thing, you have a database of stop sign images, and with the command labeled to stop when you see this thing. If I could sneak into that data set stop signs with pictures of Post-it notes on the stop sign, and I add to the label that when you see that, floor it, you'll never know, because you go out and you test your car at stop signs, it'll stop at every stop sign you come across. But that one time it sees a stop sign with a Post-it note, which is not very common, it'll floor it through the intersection. So this idea of securing the data to make sure that it's good data is going to be a very important area to overlap with cybersecurity. This is the fastest computer in the world when I was in high school. 1.8 teraflops, 1.8 trillion calculations a second. It was built out of 10,000 Pentiums, the size of a tennis court, the power of 800 homes, and it cost $55 million. This is a big red computer. This computer that we have upstairs, this is 10 times faster than that computer. 10 times faster than the fastest computer in the world when I was in high school. That's extraordinary. That's something that we can now sit FAU students at and put this brain behind that car and run experiments that the world's really never seen before. When we first started doing this, we brought some folks in who had done some of this stuff, and they said, oh, we've done this. We did this back in the 80s. I sort of scratched my head and I said, wait, you didn't even have this one. What do you mean you did it in the 80s? Like, you couldn't have done this stuff before. It just wasn't really possible because you couldn't do 18 trillion calculations a second for a few $1,000s. Right? It just wasn't practical or possible. I like this a lot. This is a punched photograph. And so this actually was the inspiration for the punch card, for the punch card computer. And this is where Herman Hollerith got the idea. And so it used to be that when you got a train ticket, what they would do to prevent train robbers and people from trading their tickets, so you don't, like 2 people will only buy 1 ticket. What they would do is they would look at you and they would punch a hole based on what you look like. Right, so I'd get this one today, but on other days I'd probably get some of the others. Right, maybe that one sometimes. And so they would look at your chops and stuff, and they'd say, "All right, you're like this." And this is a punch photograph. They called this a punch photograph. So they wanted to sort of, and then you couldn't pass the ticket behind you, kind of thing. And if it was a train robber, and this is where Herman Hollerith got the idea for a punch card. And so I have some of these. It's just kind of fun. I'm gonna pass these around. I guess we'll just kind of send some of these around. Grab a few and then pass them around. These are just kind of fun because it's just a momentum. You can kind of use all these.
Well, I heard that the Jacquard loom was basically the inspiration for this.
Exactly. So this was not the first time this technology had been used. This was used for, as Russ is saying, Jacquard loom.
If they've got round holes, they're Remingtons.
Right. So this is square holes IBM,
Yep.
and there was an electric contact that would come underneath this, and a sort of a soft brush. And if there was a hole, then the electric brush contact would go through, and it would signal a signal.
Then there was photoelectric.
Yeah, and then optical ones, absolutely. And so these were how computers ran up until like the 70s, right? I found a box of these on campus, and I just think it's kind of great to remind ourselves, how far we've come from this, right? Yeah. 2 minutes? 20 minutes. A cell phone today might have 16 gigabytes in it, right? It's not uncommon for a cell phone to have. How many punch cards is that? 200 million. 200 million. So try carrying around 200 million of these, right? And even if you had all 200 million, will it play your MP3s? right? Not at all. Not at all. So this is the punch card. And so we think about, all right, so how many different spots are there on this, right? All right, so it's 80 columns across, and there's 10 rows. So how many spots are there? 800, right? So how many different possibilities are there, right? There's 2 light switches over here. So how many combos are there, right? Both up, one down, the other one. So we get 4 combos. So we get 2 to the 800. Is that a big number? What's a big number? How big a number is that? Right?
Bigger than every molecule in the universe.
How much sand is in Boga? How many who wants to count the grains of sand on Boga? We're going to go to the beach this afternoon. How much sand's on the beach?
10 to the 21 grains of sand on the Earth.
Oh, that's good.
I looked it up
Did
last
you?
weekend.
Nice. So that's awesome.
Google.
We got to hang out. We got to hang out on the weekend. That sounds good. So you can imagine this number, right? There's a famous mathematician. He said only a math nerd would consider 2 to the 500 finite. This number is practically infinity, right? This number is more than all the atoms and all the sand on every beach, around every ocean, around every planet, around every star, in every galaxy, in the entire universe. That number doesn't even touch that number. It's much bigger than that. So let's look at what that means. If we have a simple blocky thing like this, and you think about how many images are there like of this type, this is what we're talking about this morning. Well, if we have just black and white, well, we have to look at how many squares. Here there's 64 squares. So each one has 2 choices, just like the light switch. It can be either on or off. And so I'd get 2 to the 64, already a very large number. If we make this grayscale, then we have 8 bits to represent the gray. So that means we're going to have 256 different combos. That raised to the 64 power, right? This is already a number with 154 zeros after it. It's a giant number. If we make this in color, we got 3 times 10, right? Raised to the 4,000. It's not uncommon to have a 4K monitor now, right? So these are called hyper astronomical numbers because it just swamps anything in astronomy. Astronomy doesn't come close to these numbers, right? You think about this thing has like millions of digits after it, right? This is crazy. This is crazy. So where do these? Well, we have these numbers, right? Because you have megapixel cameras. Everybody here has one of these cameras, right? In the 80s, the only people that had a digital camera would have been an astronomer. You would have had to write a grant for that thing. And so now everybody has one of these things where it's going to take 16 million numbers. And each one of those pixels is independent. So now we come back to our self-driving, right? What does that mean in terms of this car? Well, that's what we're doing. We're bringing in that pattern of the road. We think, well, there can't be that many, right? We'll just print out every road that we see, store it in a filing cabinet. When we see a road like that again, we'll go through our database and say, well, I've been here before, and we made a left. But as we see, there's just way too many. Like hyper astronomical. We couldn't print them all out in the world. Like I was saying, if I have a punch card, could I have every possible punched card? No, there's not enough material in the universe to print them all out. Like, where would they exist? You wouldn't have enough time to print them, even if you had the space. I really like this expression. Problem is too difficult to program by hand. So that something like a self-driving car, you're not going to be able to think of rules, if, then, else, while, to get this car to drive around. It's just not going to work. It's just not going to work. So amazingly, this Alvin Project is basically not much different than how the Tesla drives itself. So here we have the input of the, here they're calling it a retina. So this is the TV camera. And they digitize this every couple seconds. And then it goes through one hidden layer. So you were asking this morning, what's the difference between machine learning and deep machine learning? It's how many of these layers do you have? Do you break this down into features? And then from the features, make your decision? Or do you break those features down into features? And you can do lots and lots of layers to find subtle bits. For something like driving a car, you really only need to know there's an edge here of the side of the road. There's another edge here on the side of the road. You don't need a whole lot of detail to just stay in the lane. But that's not all we need. Lane finding is not really how we drive a car, right? There's a lot more to driving a car than just following the lanes. Right, but this thing was able to go 70 miles an hour, down the highway. This was the first version was in 88, and then they sort of redid on this one from May 94. And you can see here there's a single mono camera there. So you have to wonder why this stuff took so long to get out into the real world. So we've replicated this a couple different ways. One with our little miniature car, as you'll see upstairs. And then we also use video games to simulate this. And so here's an ancient video game I found called Car and Driver. I really like this one because all modern video games, if you sit there quietly, sort of a zombie will come out from the side and pop you on the head or something. This was a driving simulator, right? So this was a cutting edge simulator in '94. And this, sort of true to the simulation, nothing will bother you. So you can just sit here and let the clock go, and it's just a car on a track. And so actually Rodrigo did a lot of work with this one here. And so what we did is we've trained a neural network to take a look at this screen, and then we drive it around for maybe half hour or so. And in the beginning, when it's like a baby that opens its eyes, and when it first opens its eyes, it has 5 brain cells. This one only has 5 brain cells. It's not something you can do to a mouse, right? If you give a mouse only 5 brain cells, you don't have much of a mouse anymore. But this, we can have a 5 brain cell mouse, and when it opens its eyes for the first time, it thinks the world's made out of confetti. It has no idea what the world looks like. There's no structure to that. There's no features, right? It's just randomness, it's just random noise. Then it watches us drive around for about a half an hour, and we say, well, what do you think the world looks like? And it says, well, I've decided that the world has these features. It looks like this. And we can see, well, this is the edges of roads, right? These are clearly gutters and lane markings and this kinds of thing. And so it's built up, it's decided on its own that that's what the world looks like. So what's really neat is there's clouds in this world, right? If we drive around Boca and we look at the clouds, how's that going to work out? Not very well, right? So in this, it's decided the clouds don't mean anything. So sort of blue is important, red is sort of oppositely important. But this green color here and this yellow color, this says, man, this is the 0 on the weights. So we're actually seeing the weights themselves. So there was this talk about black box. We didn't know what these things looked like. Well, now with a modern computer, we can take each one of those weights and plot it like a photograph. And that's what we get here. So here we see a representation of how important it thinks that first pixel is in the top left in terms of making a decision to drive. And in fact that it made this neutral color green, this is saying that the weight there is 0. It's zeroed out the influence of that pixel. It says it doesn't matter. It doesn't matter what anything up here says. That's completely irrelevant in terms of making your driving decision. And it found that it doesn't matter what's above the horizon line.
Well, what was the feedback to the car that told it this matters, that doesn't matter?
Yeah, thank you. So I was driving this around, and I was pressing either left, right, or forward.
Okay.
So for every second, the computer would take a screenshot, just like on your phone, you can do screenshot. And then the computer, we wrote a loop that would record what button was I pressing. Was I pressing left? Was I pressing right? Was I pressing forward? And so that's the feedback. If we had asked it, we could have asked it to do other things, maybe guess the speed from a couple frames or something like that. But we asked it to turn left, right, or forward, and this decided if I want to know if the input image is appropriate for a left, right, or a forward, then I should consider the world as looking something like this. And then we can think of these as specialists, right? This one might mean turn left, and the other one might mean turn right, and the other one might mean go straight ahead. And so you can think of, you're running a business or a company, and you have 5 sort of vice presidents, and you're going to go up to your team, and you can say, all right, team, what do you think we should do? And the one says, well, I think the world looks like this, and so I say we should make a left. And the other one says, well, I think the world looks like this, and we should go forward. And then you can have another layer on top of that that's going to consider their decisions together. Any questions on that part? So this is kind of neat in that these are actually a picture of the weights, that we can look at these things like a photograph. Here's another version of the same thing. So that when it starts out, it's completely sort of confetti, has no idea what the world looks like, and then you let this run, and it decides that the world has structure like this, that it should look at these features in the world, maybe something bright here, and then a shadow there, or something shadow in the middle and bright on the outside. And then it's decided that the top half of the horizon means nothing. It's interesting to note here it found that this outside means nothing, but often we find the opposite, that it's telling us stuff's important that we didn't know. And so one of the important results that we've seen is when they looked at tumor cells from microscope data. And in medical school, the doctors are always told, just look at the tumor itself. Don't look at the cells around it, just look at the tumor, and that's how you decide. When they ran the computer on it, the computer looked at the middle, but also in this type of representation, it said, you know what, we should look at the cells around the tumor on the outside. And that actually helped with the classification. So here's an example of something that the people weren't doing. Humans thought that doesn't matter. We don't need to consider that. And here the machine has told us, wait a minute, no, we do need to be considering. So I think that's really the ultimate, that's the gold standard for this stuff. Can we have the neural network teach us something we didn't know about science?
There's the surprise.
Exactly, there's the surprise. So that would pass our Ada Lovelace test. So this is what we were sort of looking at. We have the input nodes. These intermediate nodes are going to represent the features, right? This one's telling us how much of an edge this way. That one's telling us how much of an edge this way, and so on. And then the output layer will just tell us, about the properties of this thing. So just to go back to what Elon was talking about, we might have something like for real estate where we're going to be giving it things like square feet, and houses, age of the house, and we want to know the price. But what if we have like a photograph, right? We want to take a photograph, and people go and they value houses, they look at the house, right? I can't imagine there's too many real estate appraisals who don't see, right? I don't think there's probably many blind appraisals. So this is that we've seen. Now we can take in the features, add them all up. If this thing together, these weighted, so these weights here, each one of these lines are the pixels that we were just seeing with the car edges, right, with the road. And so we can take all of these and plot them like a photograph and then see what does this thing look like. So I'd argue that this black box is just sort of not there. Okay, so we talked a little bit. I want to talk about with this next piece here. After we add these things up, we're going to take in our inputs, we're going to add them together, and then we have to kind of threshold it. And why do we want to do that? Well, imagine we had all these layers, and the first one has output some positive number, and the second one outputs a negative number, and the next one's a positive number, and so on. These things might end up canceling each other out. So we might end up where we have all of these stacks, but this first layer undoes what that one does, and so we haven't really gone anywhere. Kind of like taking 2 steps forward and 1 step back and all that, and you haven't gone anywhere. So this activation is a way of sort of sealing off what that previous layer had done and sending it to the next layer anew such that it doesn't cancel out. Another way of thinking about this is that when we add up the numbers, we're going to be adding up all the inputs. It might happen to add up to a really large number, right? Say it's 100. Neurons don't output a 100. They either fire or they don't, right? So we have to output a single number. Neurons are binary. They're either 0 or 1. They can't output like a 27 necessarily. So what we want to do is we want to map this output that we've given here to some number between 0 and 1. And so there's a bunch of different ways to do that. So these are called activation functions. And it's going to tell us how the neuron's actually going to respond based on its input. So don't worry about it. This kind of looks like a mess right now. What we want to think about this is as sort of an input and output. So let's take this first one here. What is this? Well, this is a recipe that's telling us, give us a number. You can see here it goes from -10 to 10. And then it's going to map that to a number between 0 and 1. So it's kind of a squishing function. It's a squishing function. Numbers that are sort of around the middle are just going to be a straight line, hasn't done anything like that. But numbers that get too big are just going to kind of get folded down. And numbers that are too small are going to get folded up. Because we don't want this thing to have giant, like to output an infinity. So we want to kind of cap the output of this thing. And so we kind of take the output and we sort of fold it down and fold it up so we can squash this input. So that even if this thing has a lot of input to the neuron, it's still going to output just the one. So this is called the sigmoid. This is the one we saw a lot throughout the last 30 years in literature because there's some really nice math properties with this. Tangent is nice because sometimes we want the thing to output a -1. We don't want just between 0 and 1. We want a -1. And so there we can use this hyperbolic tangent. The most common one that we're going to see nowadays is what's called the rectified linear unit. So this is just a really fancy way of saying take everything that was a negative and make it a 0. We're not going to let any negative numbers through our system. Anytime there's a negative, just turn it into a 0. So you cannot get more negative than 0. And so mathematically, we can just say it's the maximum of our number that we input and 0, whichever one's bigger. Right? You can't get smaller than 0.
And what happens if the pattern of the negative numbers tells us something that we are?
Yeah, in some cases, you might want it to output a negative number. Like this might be steering angle, where a 1 is all the way to the right and a -1 is all the way to the left. And a 0 would be stay straight. So depending on the problem that you're trying to solve, you might want these different outputs. And as you can see here with the ReLU actually can output a bigger number. So in some problems, you'd need it to output a 27 or something like that. And so this will allow you to map to larger numbers. Yeah.
Now, would it be beneficial, for example, to have, say, a tangent one that can output a negative and a positive, or 2 neurons that one controls the positive and negative and the other controls the value?
Yeah, so it's a really great point. So some things in the real world, it's hard to go negative. So you can either have one wire that can go positive or negative, or you have 2 wires, as you're saying, which one represents how positive it is, and the other represents the negative. That's actually really important for something called memristors. So in hardware, that's actually often what's done in the circuit. And these are just a couple more that you see, but these are very similar. You can imagine these do similar things as to this one here. But basically, we just want to turn off things that are negative. So this one, you can see they call this a leaky ReLU. This just helps it train a little bit better to not make it a complete 0, but to have a little bit that kind of helps you know which way to turn. So this is just the squashing. We're going to take our input and give it sort of a maximum and a minimum just so it doesn't get out of scale. If we look at what this does for like a photograph, we can take up something like this. So we can imagine this is like a photograph or some intermediate layer of the network. And we're going to apply the rectified linear unit. So this says 0.77, and that just stayed 0.77. This one says minus 0.11. That just became a 0. This one was 0.11. That just stays the same. So anything that's negative gets replaced with a 0. Anything that's not negative just stays the same. Right? So mathematically, it's really simple. Just find all of your negatives, scratch them out, and replace them with zeros. Yeah?
Do you generally have one sort of an activation function for the entire neural network, or are there different ones used for different portions?
Nowadays, you can see different ones throughout the layer, throughout the network. Yeah. Right, so it's very straightforward. Just take anything that's negative and just make it a 0.
And you can switch, let's say, the activation function from a step function to another one whenever we want, or it does it automatically?
No, it doesn't. It's not automatic. Right? This is something you'd set in the architecture ahead of time. So there's more advanced type things of how do you get that part, right? How do you do the architecture automatically? But that's a little bit different. Don't need to worry about that. And the ReLU is really important. Otherwise, sort of all your layers would just collapse down into one layer. Okay, telling me I gotta move it along. Okay, so here's our bias. Our bias is going to sort of shift things around. Normally we talked about, is this stuff bigger than 0? And if it's bigger than 0, then I'll fire. But you might say, well, it has to be bigger than 5, and then I want to fire. Or it has to be bigger than -5. In neurons, they talk about resting state potential, the sort of the rest that the neuron is and sort of what you have to overcome before it activates. And so this allows you to change essentially the sensitivity of this neuron. So when we think of a perceptron, we think of it as like, you want to think of it as like a paper cutter. You get one slice, right? It's not like scissors where you can change the angle and cut through something weird, right? It's just like a big paper cutter, and you go, and you're going to have one big slice. But you want to know, can you separate your data with just one cut? Can you make one slice through everything where it separates all the yeses on one and all the no's on the other, or maybe a little bit wrong, but overall pretty close? Problem is, most of the things in the real world aren't that organized, right? They're going to have some sort of twisty sort of curve. The boundary between the two categories is going to be very strange, right? That if you plot like, skin cancer moles versus non-skin cancer moles, it's not just going to be like, oh yeah, all the ones that are bright and orange are, are skin cancer. It's not quite that simple. So we have to think of it in different directions. So the most famous example of this is the XOR problem. So this is a very simple logic scenario when we have two inputs. When both of the inputs are off, we want it to be off. When both of the inputs are on, we want it to be off. And when one of the inputs are on, we want it to be on. And so graphically, we can look at this. We can think of this as X and Y, and then our answers as the colored dots. And so what we want is we want this to be a no, right? 0, 0 is a no. 1, 1 is a no. 0, 1 is a 1, and 1, 0 is a 1. And then you got to think, okay, where can I put my one slice? I get one neuron. I'm going to cut through this. Where do I cut such that I have all the yellows on one side of the line, all the blues on the other side? There's nowhere you can put it, right? We're going to need at least 2 cuts. So this is the idea of like, why would you ever need more than one layer or more than one neuron? Well, some problems you have to be able to, you want one cut here and one cut there. You're going to need 2 to separate these. And so that's what these types of neurons can do. Is that we have one more layer, they can detect that, and then they classify that. So as you're running these things, you're going to get a cost, right? So in the slider that Elon was showing, we have the cost for our linear fit. In our cats and dogs example, we're going to give it like a quiz. We're going to have 100 cat and dog examples. We're going to say, how many did you get right? In the beginning, it's going to start out random. It's going to be like, it's just going to guess, right? And so if you just guess on a cat and dog test, what's your answer going to be? What's your score? You're just guessing. Like 50%, right? So they'll get about 50% the first time around, right? So we can think of this as like percentage, like how many percent wrong did we get? And when you first run this thing, it's going to be like way up. It's going to be like 50%, something like that. And then what we can do is we can randomly adjust all the weights. So just randomly change all the knobs. Try it again. Did it get better or did it get worse? If it got better, we can keep it. If it got worse, try another setting. So we could do it this way. It would take a very long time. It would not be efficient. We wouldn't really solve it practically, but you could, in theory, do it this way. But the breakthrough in the last few years is automatic differentiation. It's the idea that if you're on this mountain range, what you really want to do is think of it as like a ski slope, and you have a sled, and you're just going to sit on this thing, and you just want to go downhill, right? And then maybe you'll need a chairlift to get over that piece, right?
You're talking about the gradient descent.
A gradient descent, exactly. So the real breakthrough, the reason why there's this revolution in deep learning, I don't think enough people are sort of talking about it, is this idea of automatic differentiation. That we now have a technique where we can give the computer our network, we can design any network we want, and the computer will give us a sort of a magic compass. This tells us which direction to change each knob. We have all of these parameters, right? I like to think of the control, like the soundboards in the sound studio. They have all those little knobs that they have to set. Some of the networks might have 57 million knobs. We don't know how to tune each one. But what the automatic differentiation gives us is a way of how to do that, which direction to move in. And so that's the part that's really been the breakthrough, that something like TensorFlow, the reason why you use a package like TensorFlow or PyTorch is that it gives you that, is that you can write your forward code and it will automatically give you an update about how to change the parameters. So we can build an error surface, right? So we were looking at the regression problem and we were moving the slider around. And so we think of a simple scenario, we have just the weight and a bias, just a simple, maybe a simple model like this, where we have just two parameters, and then we have these red dots, and we want a model of these. Like I want to know what is it going to be like for here. We don't actually have a red dot there. So I need this model, something that will, this green line that will go in between these dots, that will be a substitute that I can go in to an arbitrary place and say, what would the value be if I were to try a spot here? So since we have two dimensions, we have two parameters that we're trying to change, we can make a picture of this. When it gets to 57 million, unfortunately, we can't make photographs of it anymore. We can't make these animations. But if it's just two numbers, we can plot the error, how wrong this is, right? This is how many cats and dogs are misclassified. We can plot this error surface. And then what you can see is it starts out up over here being really wrong, and then we want this thing to roll downhill until it gets to the correct location. Right? You can think of this like choosing the lottery numbers, right? You have to pick what's number one, what's the first number that's going to come out of the machine, what's the second number that's going to come out of the machine. And if you could do this right in here with just, imagine there was a lottery drawing where they just pulled two things, right? And you'd want to know, okay, what's the number they're going to pick, right? That's the bluest spot kind of thing. And imagine lottery doesn't work this way, because lottery either win or you don't. You don't get like partial money for being close, right? But you can imagine what you want this thing to do is start out somewhere randomly and then roll downhill until it gets to the correct solution, sort of the winning numbers for this contest of the error surface. So what we want to do is here we have a bunch of lines, a bunch of dots that we're trying to fit with this curve. We're trying to do a regression. And so we have our input and output. And so we can see the cost at different times. And then this is going to be going downhill in this cost. So we have one parameter, P, that we're changing, right? You can see that that's basically the slope. The intercept's not changing, right? You can see it's fixed here. So we're just sweeping through one number. We're just changing one parameter at a time. And as we change that number, we can see that our cost is sort of going downhill. And that dotted line is telling us that we should keep going in that direction. And so that's what the automatic differentiation tells us. It tells us which direction to turn each knob such that this thing will go downhill in our error surface, right? This is sort of how wrong we are, and we want to be as wrong as little as possible, and so we want to move down this energy surface, right? So that's how we're going to find all of these numbers. So if we had just, imagine this is only two of these lines on here, then it would look something like this, right? But because we have more than one, we can't visualize this anymore. But we know that if we take an input, it'll break it down into features. We have our output, cat and dog. And when we find the right settings of these weights, that will work. How do we find those weights? That's what we use the gradient descent. That's what we use the automatic differentiation, which will allow us to create an error surface and then go downhill. So it's really what we've done is we've taken computer programming and we've sort of mixed it with the calculus. That we've smoothed out these computer programs so they make these landscapes. And then we want to move our solution through this landscape until we get to the cheapest spot. Right? So you think of like a skate park, right? The concrete skate park. And what this automatic differentiation is the skateboard. And when you stand on this thing, it will just take you down the natural slope of the energy surface. This is what we're going to be looking at, is how we build more layers. So tomorrow we're going to be discussing convolutional neural networks. How do we get these things to scale up better to photographs? As we give it a real photograph, this is going to be millions of inputs. So now we need lots of weights. But if you recognize something like the pen over here, and you still recognize it if I move it over there. So something about this, you can recycle the weights. And so that's what we're going to be talking about tomorrow, is how can we do weight sharing so this thing can then scale to large photographs. Ultimately, we want things like this. We want a little drone that takes in its image, breaks it down into features, just like the car and driver. It's going to break it down into sort of forest trail type features, and then finally give us an output that this thing can actually run to the motors. So I think we'll just stop with that, and then we can continue this tomorrow.